Welcome to the hidden force of the universe. What if the force that keeps your feet on the ground is also shaping galaxies billions of light years away? Welcome to a journey into gravity, the invisible power that quietly controls everything from falling objects to the motion of stars. It's a force so familiar that we rarely question it, yet so mysterious that scientists are still trying to fully understand it. In this video, you'll discover the most fascinating and mind-bending facts about gravity, from black holes that bend time, to ripples in space-time, to the strange reality of weightlessness. Each part reveals a new layer of how gravity shapes not just the universe, but your everyday life. Stay with us, and you might never look at something as simple as falling the same way again. Gravity, the invisible sculptor of the universe. Gravity is the quiet architect of everything we see and everything we don't. It is the force that binds galaxies, shapes stars, and holds your feet firmly on the ground. Yet it remains one of the most mysterious phenomena in modern science. Unlike light or sound, gravity cannot be seen directly. It does not glow, vibrate, or leave a trace you can easily detect. And yet, without it, the universe would collapse into chaos, or more accurately, never form at all. The idea of gravity as a universal force was first clearly described by Isaac Newton in the 17th century. According to his law of universal gravitation, every object with mass attracts every other object. The strength of this attraction depends on two simple factors: how massive the objects are, and how far apart they are. This elegant rule explained why apples fall from trees, why the moon orbits Earth, and why planets trace predictable paths around the sun. But gravity is not just a force, it is a storyteller of cosmic scale. Every orbit, every falling object, every tidal wave carries information about the masses involved and the invisible pull between them. When you drop a ball, you are participating in the same fundamental interaction that governs the motion of entire galaxies. Centuries after Newton, gravity was reimagined by Albert Einstein, who proposed something far more strange and profound. In his theory of general relativity, gravity is not a force in the traditional sense. Instead, it is the bending of space and time itself. Massive objects like stars and planets warp the fabric of space-time, creating curves that other objects follow. Imagine placing a heavy bowling ball on a stretched rubber sheet. Smaller balls placed nearby will roll toward it, not because of a direct pull, but because the surface beneath them is curved. This concept explains phenomena that Newton's laws could not fully describe. For example, light itself, something without mass, can be bent by gravity. When light passes near a massive object, such as a star or galaxy, its path curves. This effect, known as gravitational lensing, allows astronomers to observe distant objects that would otherwise be hidden. In a sense, gravity becomes a natural telescope, magnifying the universe. Gravity also behaves in ways that challenge intuition. On Earth, it feels constant and dependable. But in reality, gravity varies depending on where you are. At higher altitudes, farther from Earth's center, gravity is slightly weaker. This means that if you climb a mountain, you actually weigh a tiny bit less. Even more surprising, the rotation of Earth reduces the effective pull of gravity at the equator compared to the poles. These differences are small, but measurable with precise instruments. Perhaps one of the most fascinating aspects of gravity is its incredible weakness compared to other fundamental forces. A small magnet can lift a paperclip against the entire gravitational pull of Earth. Yet, gravity dominates the large-scale structure of the universe. Why? Because it only attracts, it never repels. Over vast distances and enormous masses, this constant attraction accumulates, shaping galaxies, clusters, and the cosmic web itself. Despite centuries of study, gravity still holds secrets. Scientists continue to search for a theory that unifies it with the other fundamental forces of nature. They explore extreme environments, like black holes and the early universe, where gravity behaves in ways we don't fully understand. Each discovery brings new questions, reminding us that gravity is not just a solved problem, but an ongoing mystery. In the end, gravity is both familiar and profoundly strange. It is the reason you can stand, walk, and live on Earth, yet it also governs the motion of stars billions of light-years away. It connects the smallest human experience to the grandest cosmic structures, acting as a silent thread woven through the entire universe. When gravity gets extreme, black holes, time, and the edge of reality. If gravity is the quiet sculptor of the universe, then black holes are its most dramatic masterpieces. These objects represent gravity pushed to its absolute limit, regions of space where the pull becomes so intense that nothing, not even light, can escape. The concept of a black hole naturally emerges from the equations of Albert Einstein, yet for decades they were considered purely theoretical. Today, they are among the most studied and most fascinating objects in the cosmos. A black hole forms when a massive star collapses under its own gravity at the end of its life. Without enough outward pressure to counterbalance the inward pull, the star's core shrinks to an incredibly small point known as a singularity. Around this point lies the event horizon, the boundary beyond which escape is impossible. Crossing this invisible line means being forever cut off from the rest of the universe. It is not a surface you can see or feel, but a threshold defined entirely by gravity. One of the most mind-bending effects near a black hole is the distortion of time itself. According to general relativity, gravity doesn't just affect motion, it affects time. The stronger the gravitational field, the slower time passes. Near a black hole, this effect becomes extreme. To a distant observer, a clock falling toward the event horizon appears to slow down, ticking more and more slowly, never quite reaching the edge. In contrast, for the object falling in, time feels completely normal. This phenomenon, known as gravitational time dilation, reveals that time is not universal, it is shaped by gravity. This warping of time leads to fascinating and sometimes unsettling possibilities. In theory, if you could orbit close to a black hole and then return to Earth, you might find that far more time has passed for everyone else than for you. This is not science fiction. It is a real prediction of physics, and it has been experimentally confirmed on smaller scales using precise atomic clocks on Earth and in orbit. Near a black hole, the effect would be dramatically amplified. Black holes also challenge our understanding of information and reality. When matter falls into a black hole, what happens to the information it contains? According to classical physics, it seems to disappear forever. But this creates a paradox, because the laws of quantum mechanics suggest that information cannot be destroyed. Scientists are still working to resolve this conflict, making black holes a key battleground for unifying gravity with quantum physics. Despite their reputation as cosmic vacuum cleaners, black holes do not simply suck in everything around them. From a safe distance, they behave like any other massive object. If our Sun was suddenly replaced by a black hole of the same mass, Earth would continue orbiting almost exactly as before, though without sunlight, life would quickly vanish. It is only when you get close that their extreme nature becomes unavoidable. In recent years, black holes have moved from theory to observation. In 2019, scientists working with the Event Horizon Telescope captured the first image of a black hole's shadow, located in the galaxy M87. This groundbreaking achievement provided direct visual evidence of something that had existed only in equations and simulations. Later observations revealed another image, this time of the black hole at the center of our own galaxy, the Sagittarius A star. Perhaps the most poetic aspect of black holes is how they redefine the limits of knowledge. The event horizon marks not just a physical boundary, but a boundary of understanding. Beyond it, the known laws of physics break down, and our current theories can no longer fully describe what happens. Black holes remind us that gravity is not just a force, it is a gateway to deeper mysteries about space, time, and the nature of reality itself. Gravity without weight, the strange reality of free fall and orbit. At first glance, gravity seems simple, it pulls things down. But this familiar experience hides a deeper and more surprising truth. In the strange language of physics, gravity is not always something you feel. In fact, under certain conditions, gravity can seem to disappear entirely, even when it is still fully present. This paradox lies at the heart of one of the most important insights in modern science, first clearly understood by Albert Einstein. Imagine stepping into an elevator whose cables suddenly snap. As the elevator falls, everything inside it, people, objects, even the air, falls together at the same rate. For a brief moment, you would feel weightless, as if gravity had been turned off. But gravity is still there, pulling everything downward. The reason you feel no weight is because there is no resistance force pushing against you. This state is called free fall, and it reveals that what we experience as weight is not gravity itself, but the force of the ground or floor pushing back against us. This idea leads directly to the concept of orbit. When an object moves sideways fast enough while falling toward a planet, it never actually reaches the ground. Instead, it continuously falls around the planet, tracing a curved path. This is exactly what the Moon does around Earth, and what satellites do as they circle our planet. They are not floating because gravity is absent, they are in a constant state of falling, perfectly balanced between motion and gravitational pull. Astronauts aboard the NASA spacecraft or the International Space Station experience this phenomenon every day. Inside the station, everything appears to float. Tools drift, water forms spheres, and astronauts glide effortlessly through the air. This environment is often called zero gravity, but that term is misleading. Gravity at the altitude of the space station is still about 90% as strong as it is on Earth's surface. The sensation of weightlessness comes entirely from being in continuous free fall around the planet. The physics of orbit reveals a delicate balance. If a satellite moves too slowly, it will spiral downward and eventually re-enter the atmosphere. If it moves too fast, it can escape Earth's gravity entirely and travel into deep space. There is a precise speed, called orbital velocity, that allows an object to remain in stable orbit. For low Earth orbit, this speed is about 17,500 miles per hour, 28,000 kilometers per hour. At this velocity, the curvature of the object's path matches the curvature of Earth itself. One of the most fascinating consequences of orbit and free fall is how they reshape our understanding of direction. On Earth, down always points toward the ground beneath your feet. But in orbit, there is no true up or down. Everything is falling together, so traditional directions lose their meaning. Astronauts can orient themselves in any direction, and floor and ceiling become arbitrary labels rather than physical realities. Free fall also reveals subtle effects that are usually hidden in everyday life. For example, if you drop two objects of different masses in a vacuum, they fall at exactly the same rate. This principle, known as the equivalence of gravitational and inertial mass, was a key clue that led Einstein to develop general relativity. It suggests that gravity is not a conventional force acting differently on different objects, but a fundamental property of space-time affecting all motion equally. Perhaps the most profound insight from all of this is that gravity and motion are deeply intertwined. What feels like floating is actually falling. What appears to be stillness is often constant motion along a curved path through space-time. These ideas challenge our everyday intuition, yet they describe the true nature of how objects move in the universe. In the end, gravity is not just about being pulled down, it is about how objects move when nothing stops them. Free fall and orbit reveal a hidden simplicity beneath the complexity of motion. Everything follows the natural curves of space-time. And in those curves, the universe quietly unfolds. Gravity waves. When the universe itself trembles. For centuries, gravity was thought to act silently and instantly across space. But modern physics reveals something far more dynamic. Gravity can move, ripple, and carry energy across the universe in the form of gravitational waves. These waves are not like sound or light, they are vibrations in the very fabric of space-time itself, stretching and compressing everything they pass through. Predicted by Albert Einstein in 1916, gravitational waves remained purely theoretical for nearly 100 years. The idea is both simple and extraordinary. When massive objects accelerate, especially in violent cosmic events, they disturb space-time, sending out ripples that travel at the speed of light. Imagine dropping a stone into a still pond. Waves spread outward from the point of impact. In a similar way, when two black holes collide or neutron stars spiral into each other, they create waves that propagate across the cosmos, carrying information about their origin. These waves are incredibly subtle by the time they reach Earth. Even the most powerful gravitational waves distort space by less than the width of a proton. Detecting such tiny changes requires instruments of astonishing precision. This challenge was finally overcome in 2015 by the LIGO scientific collaboration, which made the first direct detection of gravitational waves. The signal came from two merging black holes over 1 billion light-years away, a cosmic event so powerful it briefly outshone all the stars in the observable universe combined, in terms of gravitational energy. The detection of gravitational waves marked the beginning of a new era in astronomy. Until then, scientists had studied the universe primarily through electromagnetic radiation, visible light, radio waves, X-rays. Now, gravitational waves offer a completely different way of observing cosmic events. They allow us to listen to the universe, capturing phenomena that might otherwise remain hidden, such as black hole mergers that emit little or no light. One of the most remarkable discoveries came in 2017, when gravitational waves from colliding neutron stars were detected alongside a burst of light observed by telescopes around the world. This event confirmed that heavy elements like gold and platinum are forged in such collisions. In a very real sense, the atoms in your jewelry, and even in your body, owe their existence to these distant, violent encounters shaped by gravity. Gravitational waves also provide new tests for our understanding of physics. By analyzing their patterns, scientists can verify predictions of general relativity under extreme conditions. So far, Einstein's theory has passed every test with remarkable accuracy. However, researchers continue to search for subtle deviations that might point to new physics beyond our current theories. What makes gravitational waves truly extraordinary is their ability to pass through matter almost completely unaffected. Unlike light, which can be absorbed or scattered, gravitational waves travel across the universe with minimal interference. This means they carry pristine information from their source, offering a direct glimpse into events that occurred billions of years ago. As detectors become more sensitive, scientists expect to uncover an even richer soundscape of the universe. The steady hum of countless distant mergers, the echoes of the early universe, perhaps even signals from unknown cosmic phenomena. Each detection adds a new piece to the puzzle, revealing a universe that is not silent, but alive with motion and vibration. In the end, gravitational waves transform our understanding of gravity from a static force into a dynamic, ever-changing phenomenon. They show that the universe is not just shaped by gravity, it resonates with it. And in those faint, passing ripples, we find a new way to explore the deepest mysteries of existence. Gravity across the cosmos, from galaxies to dark matter. Gravity does not stop at planets or stars. It operates on the grandest scales imaginable, shaping the structure of the entire universe. When we look deep into space, we see galaxies gathered in clusters, clusters forming superclusters, and vast filaments stretching across billions of light-years. This immense cosmic web exists because of gravity, slowly pulling matter together over billions of years, turning tiny fluctuations after the Big Bang into the vast structures we observe today. At the scale of galaxies, gravity governs the motion of billions of stars. Our home galaxy, the Milky Way, is held together by the mutual gravitational attraction of its stars, gas, and unseen components. Stars orbit the galactic center much like planets orbit a star, but there is a mystery: they move far faster than expected. According to visible matter alone, galaxies should not have enough mass to hold themselves together at those speeds. Yet they remain stable, suggesting that something invisible is adding extra gravitational pull. This unseen component is known as dark matter. Although it cannot be directly observed, its presence is inferred through its gravitational effects. Galaxies rotate as if they are embedded in massive halos of invisible matter, extending far beyond their visible edges. Dark matter does not emit, absorb, or reflect light, making it extraordinarily difficult to detect. However, its gravitational influence is undeniable, shaping the formation and evolution of galaxies across the universe. Evidence for dark matter also comes from gravitational lensing, where massive objects bend the light of more distant sources. In some cases, the amount of bending observed is far greater than what visible matter alone can account for. This suggests that large amounts of unseen mass are present, warping space-time in ways that reveal their existence indirectly. Through gravity, we can see what would otherwise remain completely hidden. On even larger scales, gravity competes with another mysterious force: dark energy. While gravity pulls matter together, dark energy appears to drive the expansion of the universe apart. Observations show that the universe is not just expanding, but accelerating in its expansion. This means that, over vast distances, the repulsive effect of dark energy can overcome the attractive force of gravity, leading to a dynamic and ever-changing cosmic balance. Galaxy clusters provide some of the most dramatic evidence of gravity's power. These enormous structures, containing hundreds or thousands of galaxies, are bound together by gravity and filled with hot gas emitting X-rays. When clusters collide, they create some of the most energetic events in the universe. By studying these collisions, scientists can map the distribution of dark matter and better understand how gravity operates on colossal scales. One of the most famous examples is the Bullet cluster, where two galaxy clusters have passed through each other. Observations show that the visible matter, mainly hot gas, was slowed down by the collision, while most of the mass, inferred from gravitational lensing, passed through unaffected. This separation provides strong evidence that dark matter exists and interacts differently from normal matter. Despite all these discoveries, the true nature of dark matter remains unknown. Scientists have proposed various candidates, from exotic particles to modifications of gravity itself. Experiments around the world are searching for direct evidence, but so far, dark matter continues to elude detection. It is one of the greatest unsolved mysteries in physics. In the end, gravity reveals a universe far more complex than it first appears. It not only binds stars and galaxies, but also exposes the presence of invisible components that dominate the cosmos. Through its influence, we uncover structures, forces, and mysteries that challenge our understanding and push the boundaries of science. Gravity, once thought to be simple, turns out to be the key to unlocking the hidden architecture of the universe. Gravity on Earth, the force that shapes everyday life. While gravity governs the motion of galaxies and black holes, its influence is just as profound in our daily lives. On Earth, gravity is the constant force we rarely notice, until we stop to think about it. Every step you take, every drop of rain that falls, every object that stays firmly in place is a result of Earth's gravitational pull. It is so familiar that it feels ordinary, yet it is quietly shaping nearly every aspect of the world around us. The strength of gravity on Earth depends on the planet's mass and size. Our planet is massive enough to hold a thick atmosphere, keep oceans bound to its surface, and maintain stable conditions for life. Without sufficient gravity, air and water would drift off into space, as has happened on smaller worlds like the Moon. This delicate balance makes Earth uniquely suited to support complex ecosystems. Gravity also gives weight to objects, but as we've seen, weight is not the same as mass. Mass is the amount of matter in an object, while weight is the force exerted on that mass by gravity. This is why you would weigh less on the Moon, where gravity is about 1/6 as strong as on Earth, even though your mass would remain exactly the same. The difference highlights how gravity connects physical properties to the environment in which they exist. One of the most visible effects of gravity on Earth is the behavior of water. Rivers flow downhill, rain falls from clouds, and oceans form vast, level surfaces that follow the curvature of the planet. Gravity pulls water toward Earth's center, creating pressure in the depths of the oceans and driving the water cycle that sustains life. Even the tides, those slow, rhythmic rises and falls of sea level, are shaped by gravity, primarily through the interaction between Earth and the Moon. Gravity also plays a crucial role in how our bodies function. It influences blood circulation, muscle strength, and bone density. Over time, the human body has adapted to Earth's gravity, developing systems that rely on its constant pull. When astronauts spend extended periods in space, they experience muscle loss and weakened bones because their bodies are no longer working against gravity in the same way. This highlights how deeply gravity is woven into biology itself. Even the shape of Earth is determined by gravity. While often described as a perfect sphere, our planet is actually slightly flattened at the poles and bulging at the equator. This shape, known as an oblate spheroid, results from the balance between gravitational forces pulling inward and rotational forces pushing outward. Gravity ensures that large objects like planets settle into rounded shapes, minimizing their energy and creating stable structures. Gravity is also essential for stability in our environment. It keeps the atmosphere layered, allowing weather systems to form and evolve. It ensures that objects return to the ground after being lifted, creating predictable motion that humans have learned to use in everything from sports to engineering. From the arc of a thrown ball to the flight of an airplane, gravity is always present, influencing motion in ways both subtle and obvious. Despite its familiarity, gravity on Earth is not perfectly uniform. It varies slightly depending on location, altitude, and the distribution of mass beneath the surface. Mountains, ocean trenches, and variations in Earth's density all create small differences in gravitational strength. These variations are measurable and are even used by scientists to study the internal structure of the planet. In the end, gravity is not just a cosmic force, it is a foundation of everyday experience. It shapes landscapes, governs motion, and supports life itself. Without it, the world as we know it would not exist. And yet, because it is always present, it often goes unnoticed, a silent force that defines reality from the ground beneath your feet to the air above your head.